After studying this module, you will be able to know about carboranes, type of carboranes, and learn about various methods of preparation of carboranes. The closely related to the polyhedral boranes and borohydrides are the carboranes, more formally the carboranes, a large family of clusters that contains boron and carbon atoms. Thus, carboranes are mixed hydrides of carbon and boron in which both carbon and boron atoms exist in electron deficient molecular skeleton. Carboranes are also defined as the electron delocalized boron framework containing one or more carbon atoms. These molecules are non-classical as the skeletal carbon and boron atoms are involved in delocalized bonding, each typically having 5 or 6 neighbors. Now we shall have a look at the carboranes and their general routes of preparation. Carbon has one more electron than boron. So, the CH moiety is isoelectronic with the BH negative or BH2 species. An isoelectronic relationship also exists between C and BH or B negative. Hence, it is possible to replace a boron atom in a borane with a carbon atom with an increase of 1 unit positive charge and retain an isoelectronic system. The polyhedral carboranes may be considered as formally derived from the BnHn2- ions in which a BH unit has been formally replaced by an isoelectronic CH unit. Each CH group is regarded as donating 3 electrons to the framework count. Thus, 2 such replacements lead to neutral molecule of general formula Bn-2 C2Hn. All such carboranes from n equals to 5 to 12 are known either as such or for n equals to 8 to 10 as CC dimethyl derivatives. The isomeric forms of these carboranes are possible in all the cases. The range of composition in carboranes cages extends from boron-rich clusters such as C2B10H12 and CB11H12- to systems having as many as 6 skeletal carbon atoms, but those with high boron content are dominant. The borane anions B10H10-2- and B12H12-2- have been studied far more thoroughly than the others because of their stability. The best studied system is C2B10H12 isoelectronic with B12H12-2-. Other dicarboranes are derived from the corresponding pentaborane 5 B5H5-2-, C2B3H5, hexaborane 6 B6H6-2-, C2B4H6, heptaborane 7 B7H7-2-, C2B5H7, octaborane 8 B8H8-2-, C2B6H8, nonaborane 9 B9H9-2-, C2B7H9, and decaborane 10 B10H10-2-, C2H8H10. Dianions B11H11-2-, C2B9H11. The C2B9H11-2- anions are known by the trivial name of dicarbolide ion from the Spanish olla a pot, reflecting the pot-like shape of C2B9. The carboranes conform to the electronic rules similar to those for boranes and are also known as closo, nido and arachno structures, which can formally be regarded as the derivatives of BnHn+2 or the related anions Bn BnHN2-, BnHN plus 4 and BnHN plus 6 respectively. The chlorocarboranes have the general formula CaBn-A HN-A plus 2 and are bonded by N plus 1 skeletal pairs of electrons. The most common members of the class have A equals to 2, that is C2Bn-2 HN, and one or both of the carbon can be replaced by the isoelectronic B- to give CBn-1 HN plus 1. The nidocarboranes have the general formula CaBn-A HN-A plus 4 and are bonded by N plus 2 skeletal pairs of electrons. Again, carbon can be replaced by B- or BH to give compounds, all of which are skeletally isostructural with BnHN plus 4. The arachnocarboranes are present less numerous than the other two classes. These are characterized by general formula CaBn-A HN-A plus 6 and are bonded by N plus 3 skeletal pairs of electrons. These are structurally related to BnHN plus 6, that is A equals to 0. For example, C2B7H13 is related to B9H15 and B9H14- ion. Now, let us have a look at the preparative routes. The reactive boron hydrides B2H6, B5H9 and B10H14 are used as starting materials to synthesize carboranes, which may be handled safely and be suitable for the use as high energy rocket and jet fuels. The boron hydride alkyne reaction is the most important route to carboranes. The alternative preparative methods are used in view of cost, safety and availability of borane starting materials. The carborane synthesis involves insertion of carbon into polyborane framework, as boranes provide the required electron delocalized matrix. The preparative chemistry of carboranes can be described as follows. Number 1, for the chlorocarboranes that are small and intermediate sized and ortho, meta and para carboranes. Small chlorocarboranes include CN-BnHN plus 2, N from 3, 4 and 5 and CB5H7, and intermediate sized chlorocarboranes are CN-BnHN plus 2, where N ranges from 6, 7, 8 and 9. Small chlorocarboranes not larger than C2B5H7 in appreciably yield are formed by A. High energy reactions between boranes and alkynes, B. By conversion of nidocarboranes, C. By pyrolysis and electric discharge in alkyl boranes, and D. By reaction of boranes with carbon vapors. The alkylated derivatives can also be prepared by A. The reaction of alkyl boranes with alkynes, B. The hydroboration of alkylyl boranes, C. The dehalogenation of alkyl boron halide with alkali metals. Now, we will look at the borane-alkyne gas phase reactions. The interactions of the lower nidoborane hydrides with acetylene in vapor phase under high energy conditions such as electric discharge or flash reactions is an inefficient method to obtain characterizable carboranes as complex mixtures of small chlorocarboranes such as C2B3H5, C2B4H6 and C2B5H7, along with their methyl and ethyl derivatives, and non-volatile amorphous CX, BY, HZ solids are formed. This is shown in the following reaction, where nido B5H9 reacts with acetylene at 500 to 600 degrees Celsius gives rise to chloro 1,5C2B3H5 plus chloro 1,6C2B4H6 plus chloro 2,4C2B5H7. Now, we will look at the borane-alkyne reactions in solutions. In order to obtain the carboranes in high yield, the reactions of borane hydrides with alkynes are undertaken in solvents such as 2,6-dimethylpyridine and triethylamine. The nido RR-C2B4H6 derivatives, where R and R prime can be hydrogen, alkyl, alkenyl or phenyl, have been prepared from the reactions of B5H9 with alkynes in 2,6-dimethylpyridine at room temperature. The chlorocarboranes of compositions R2, C2, B10, H10 are synthesized from the reactions of 6,9-L2-B10H12 derivatives of decaborane, where L is a Lewis base with alkynes in the organic solvents. It is shown in the reaction 6,9-L2-B10H12 plus an alkyne gives rise to chloro RR prime C2 B10H10 plus 2L plus H2, where R can be hydrogen or an alkyl group. Pyrolysis. Pyrolysis of nido or arachnocarbaboranes or their reaction in a silent electrical discharge leads to closed species either by loss of hydrogen or disproportionation. That is, C2BNHN plus 4 gives C2BNHN plus 2 plus hydrogen, and twice C2BNHN plus 4 gives C2BN minus 1 HN plus 1 plus C2BN plus 1 HN plus 3 plus twice hydrogen. The pyrolysis of alkyl boranes at 500 to 600 Celsius is particularly useful for the preparation of monocarbaboranes, though the yields are often low. Example, 1,2-Me2 nido B5H7 gives chloro 1,5C2B3H5 plus chloro 1CB5H7 plus nido 2CB5H9 plus 3-Me nido 2CB5H8. Now, looking at the cluster expansion reactions. The cluster expansion reactions with diborane provide an alternative route for the preparation of intermediate chlorocarboborane. Example, chloro 17C2B6H8 plus half P2H6 gives chloro 16C2P7H9 plus hydrogen, and chloro 16C2B7H9 plus half P2H6 gives chloro 16C2B8H10 plus hydrogen. Now, looking at the isomerization. The three isomeric icosahedral carboranes with orthocarborane 12C2B10H12, metacarborane 17C2B10H12 and paracarborane 112C2B10H12 are unique both in their ease of preparation and their stability in the air. Of these, an extensive chemistry has been developed for 1,2 isomer in particular. The direct reaction of ethine or acetylene with decaborane in the presence of a Lewis base, preferably Et2S, affords the bulk synthesis of chloro 1,2 isomer. That is, nido B10H14 plus twice SET twice gives B10H12 SET2 twice plus hydrogen, and B10H12 SET twice whole twice plus the acetylene molecule gives chloro 1,2C2 B10H12 plus twice SET twice plus hydrogen. The heating of 1,2 isomer in the gas phase at 470 degrees Celsius for several hours leads to the formation of 1,7 isomer. The quantitative yield is obtained by flash pyrolysis at 600 degrees Celsius for 30 seconds. A heating of the 1,7 isomer for a few seconds at 700 degrees Celsius results in the formation of 1,12 isomer with 20% yield. Figure shows the isomers of clozo C2B10H12. The diamond square diamond mechanism has been proposed for the 1,2,1,7 isomerization, but the 1,12 isomer cannot be generated by this mechanism. An alternative mechanism giving both the 1,7 and 1,12 isomers is the successive concerted rotation of the three atoms on a triangular face. A third possible mechanism involves the concerted basal twisting of two parallel pentagonal pyramids comprising the icosahedrons. The different proposed mechanisms may be considered to be active simultaneously. Now we shall have a look at the nido-carboranes. The characterizable gas or liquid products with nido 2,3C2B4H8 and nido 1,2C2B3H7 are open cage carboranes with the formation of minimal amorphous solids are formed from the vapor phase Borane-Alkyne reactions under mild conditions. Nido B5H9 with acetylene at 200 degrees Celsius gives nido 2,3C2B4H8. Metal acetylides can also be used in lieu of alkynes to obtain dicarbon or monocarbon carboranes, that is LiC triple bond CCH3 plus nido B5H9 gives C2H5 CB5H7. The large nido carborane anions such as CB10H13 minus, CB10H11 3 minus, 1,2 and 1,7 C2B9H12 minus and C2B9H11 are also known. Now we will look at the arachnocarboranes. Looking at the cluster degradation reactions, a few arachnoboranes have been prepared and characterized, of which the first to be prepared was 1,3-dicarbo-nanoborane 13, 1,3-C2B7H13, which was obtained as a degradation product when 2,3-C2B9H11 was treated with chromic acid. The C-phenyl, C-methyl and C-C-dimethyl derivatives are also known, and the structure of dimethyl derivative has been established by X-ray analysis. The cluster degradation reactions lead to more open structures. Example, clozo 1,6C2B8H10 in the presence of undergoing base hydrolysis gives arachno 1,3C2B7H12 minus plus BOH thrice. Clozo 2,3C2B9H11 under the chromic acid oxidation gives arachno 1,3C2B7H13 plus twice BOH thrice plus 5H plus. Now we shall summarize what we have learnt in this module. The evolution of carborane chemistry is related to their applications in drug design, liquid crystal nanostructure construction, crystal engineering and incorporating the thermally stable carborane residues 1,7C2B10H12 in high polymers such as silicones in order to increase the thermal stability. The prefixes clozo, nido and arachno are also used for carboranes similar to those for boranes, being the derivatives of BnHn plus 2, BnHn plus 4 and BnHn plus 6 respectively. The boron hydride alkyne reaction is the most important reaction for the preparation of carboranes. The small nido-carboranes can be prepared by the reactions of boranes with alkynes under milder conditions than those used to form clozo-carboranes. Clozo-carboranes are the most numerous and the most stable of the carboranes.